today we're going to pick off where we left off last time, where we did an implementation of the bug around toProperty key in the interpreter using bytecode. And we discussed what bytecode is and how it works, and also a few debugging tools that were also new to me. And we walked through those, saw how they worked. That was really cool, also for me to learn. Today we're gonna fix that implementation because it's broken. And then we are going to implement it in the first, we're not quite, it's kind of like getting into the gist. We're going to implement them in the next layer. So we started off in the interpreter, and now we're going to go into something called the baseline interpreter. And we're going to talk about the difference between interpreters and compilers. And to help us with that, I've created a little repository called TwitchMonkey. So if you want to check it out, if you haven't had a chance yet, you can check it out during the stream or after the stream. But this is a tiny engine for a tiny language that doesn't do anything. It just helps us see a simplified version of what SpiderMonkey is doing, so that when we look at the SpiderMonkey code, we have a clear idea of what's going on there. So, for those of you who are new, maybe you haven't seen this series before, or you just saw it pop up on your timeline, what we're doing in Compiler, this Twitch stream, is we are working on the SpiderMonkey compiler to implement fixes around the JavaScript specification to make the SpiderMonkey compiler closer to the JavaScript specification ECMA 262. Oh, and I forgot to put on my light. There you go. Maybe you can see me better now. Right, so just as a quick reminder, if I can move my mouse, we're working on this bug, which will appear for you in just a second. So this is the bug that we've been working on for the last 5 weeks, so quite some time. And we have a partial implementation there. And I'm going to show you what we did last week and walk you through what it was and also what I got wrong while I was doing it. So we were in the interpreter. Okay, so here's what we did last time. So we're implementing a new bytecode, a new shorthand for the computer to read, for the interpreter to read, that's really lightweight. It's basically just a few bytes to do this action of setting the element. Now, to remind people what the bug is, because we do have some new people, we have a bug. Let me see if I can find it. Super simple. Yeah, we've got Andre's example here. So you see this piece of code here that's null, accessing the 0 property on null, and then incrementing that by 1. The problem with this code, in particular, if, for example, we do ++ null 0, this code evaluates these things in the wrong order. That's the fundamental problem that we have here. For example, if we have a function, some kind of a function like throw some error, what should happen is we should get throw some error is not defined. So you see what's happening in the console here. We're getting an error here instead of, if we do the increment, instead of here, where we're getting an error on null not having any properties. So the order of operations that we had, the order of instructions that we were following, is inconsistent between these two expressions, only because of this increment operator. And what we want to do is we want to make it consistent. JavaScript should work in a predictable way, and this is how it's specified. So that's what we've been working on for 5 weeks. And today we're going to finally start looking at the barrier between, so before we implemented it entirely in the front end using existing bytecodes. And I should have had toilet paper available. I actually wanted to show this. So let me find something that'll do in a pinch. Damn. All right, so I don't know if you can see that very well, but these are 3 layered things. What we had were 3 things on a stack, and we swapped the top 2 like so that we could test this element and then swap them back so that we could use this element. That's very abstract. Maybe I'll draw it, because new folks, let's make sure everybody's on board. Let's draw what the thing was. Okay, so I'll add a layer and hide this. Okay, so we have a stack of bytecodes. Oh, I'm not used to drawing yet. We have a stack of bytecodes that are doing things. And the way that bytecodes work is you can have a number like 1 push to the stack, a number, and then an add. And then what the bytecode will do is it'll look at this one, and then it'll do an operation. And we'll see that in a second. What we were doing with our bytecode is we had an operation that said check. This isn't big enough. Let's make it bigger. We want to check if null. And then the next thing that we did was, what was the order of this originally? Ah, yeah, I think this was a problem. Evaluate key. And then check if null, and we needed to replace these. And what we had on the stack was check if null depends on the object being there, but we couldn't have it there anymore. I'm not making any sense right now. You know what? It's going to be easier if I just show you everything. Okay. It's always easier to look at stuff actually work. Now I should already have a running version. So, oh no. Oh yeah, I introduced a crash. Okay, now it should work. Can everybody see this? Yes. Okay, so we can disassemble a little thing that does the code that we're looking at. So I'm running this inside of the interpreter, only the interpreter, and this is inside of the JavaScript shell. And there we go. That's what I wanted to show you. So here we have a stack. This is the bytecode that's being emitted. And what we needed to do was we needed to originally the implementation had, like, we would take one argument, swap it, and then swap it again so that we're looking at the right values on the stack. Sorry, if this is very abstract, please watch, I believe it's episode 2, and it should become very clear. We have for those of you who are new, we have a disassembly function that helps us look at the bytecode that's being emitted for the piece of code that we're investigating. Okay, cool. Now, we had some problems in our initial implementation. Let's take a look at those. So last week, we looked at this case statement. And before I dig into this, I want to talk about what an interpreter actually is. So, and that's what this little project that I made for you all, this Twitch monkey, that's what that's for. So what is an interpreter? An interpreter is essentially like one really big for loop. Like, oh, I'm not showing you the right thing. Ding. Okay, so it's one really big for loop. So it's for, and then just case statements all the way down. And then the compiler actually uses the same sort of instructions and bytecode. It shares a lot of things with the interpreter, but what it does is it outputs a script, a custom script that can be run much more quickly. And then the interpreter, it says, okay, have I seen this before? Yeah, can't write very well. Have I seen this before? If I have, go run the script. And if I haven't, go through this for loop. And from the outside, it might look like, well, we've got a for loop no matter what. Like, why is there such a difference? But you can really see it when we step through the code. So that's going to be easier to show in a really controlled environment. So let's go to the little JavaScript-based interpreter and compiler that I wrote and see what happens there. Okay. So you can find this project over here. It's called TwitchMonkey because everything's a monkey. And there's a file called engine, and it does everything. It actually takes care of all of the steps that you would expect to do in a regular engine. And it mimics very closely what we do in our engine. So let's start piece by piece, like function lex. A lexer basically, well, it's a lexer or tokenizer. It splits up the text of your code into smaller pieces. And I have a working version here. We can take a look at it here. Lex takes some kind of a string. Now, the string that Lex can take is defined by the really tiny language that I specify here in the README. It's really not exciting. It doesn't do anything. And I think that's important because since it doesn't do anything, we can just see how the thing is built rather than look at the details of how things are implemented. So our lexer is going to only take, based on our definition here, it only takes 4 inputs, which is A, B, C, and D. That's our tiny language. It doesn't have any functionality other than printing stuff. So we have, we can put any number of A's and B's. We can go like A, B, whatever. All of these are valid languages. And the lexer will split it up into individual tokens, which are just capitalized versions of the letters. In a real tokenizer, you'll probably have a tuple where you have the type, the token type. We call it token kind in our code base, and some data associated to it. Then we can also take that stuff and we can do what? We can do what with it? We can parse it. So let's say we've got A, B, A, B. This is the code that we want to run. And when we run it, what we get back is our bytecode. Now, this obviously isn't real bytecode. It's just an X in front of an A or a B. But it outputs basically, we're calling this bytecode. And in my implementation, I've skipped the AST because the language that we're working with has no structure. So all this parser is a loop. It's a for loop with a switch statement that covers all of the tokens, plus it throws errors. The responsibility of the parser is to structure the code in a way that can be reliably executed. So like any kind of information that might be rearranged in order to make the code more human readable, because the purpose of programming languages is to be human readable, those become simplified so that the machine can learn them, can read them. And this is done through just a big switch statement. That's all that the parser does. Rather than outputting bytecode, it's outputting an AST, and then the bytecode emitter is outputting the bytecode. We've combined those two things into the same step, and once we leave the bytecode emitter, we've exited out of the front end of the engine. And the front end's responsibility is structuring the code in a way that the machine can read it and to throw errors. So for example, we can throw invalid stuff. For example, if instead of giving it valid bytecode, or actually I can't give it invalid strings because my code doesn't allow invalid strings, but for example, let's say we give it the wrong kind of bytecode, it'll throw and say that it's invalid. And that's where a lot of like your early errors in JavaScript come from. They come from this layer. Next, we have the interpreter. So what we can do is we can interpret this code that we've been running. Like so, and we get duck, goose, duck, which is the functionality of this language as specified. So if you read the specification, we are printing either goose if it's an A and duck if it's a B, and then other things. And that's what the interpreter is doing. So we're going to ignore this bit of the code for now. And we're going to look just at this for loop because, again, interpreters are basically just one giant for loop that's going over all of the different cases in the code, all the different bytecodes that we've given, and running instructions on them. In this case, the instruction is just console log. But let's take a look at what that looks like in the engine itself, the actual SpiderMonkey engine. And here we are. We have the beginning of the case statement for prepare set element, which we added last week, and the end. And we have a set of instructions here of what we're going to do with prepare set element. That's it. And that's true for the entirety of the interpreter. So, for example, where does it start? Thought it was higher up. Where's the first case statement? You get the idea. Okay, so that's what an interpreter is. It's a giant case statement that goes through and implements each of the instructions as it sees the bytecode. So let's go back to the code and keep reading. So this is great, but this might be really, really slow. So let's actually add a debugger statement in here and see what this looks like. Let's make that a little smaller because I can't see what it's doing. So, okay. Let's run that again. So we start at the beginning of the loop, and we take a look at what the code is, and the code is XA, so we're going to go into this first case statement. And then when we step, we do the console log, we break, and then we go back to the top of the for loop. Now the code is B. We're going to go to this case statement, step. Here's the case statement we're in. We're going to log, and then we're going to go back to the top. Our code is now XA, and then we go to console log instruction A. So that's okay, but we're only working with 3 elements right now. What if what we're looking at is something like, I don't know, something really, 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 really long. Actually, let's make it even longer. Now, stepping through this is going to be awful. Right? This is going to take a long time to get through. So this is a limitation of interpreters because they have to for every single time that they run the program, they have to interpret it anew, even if, say we run this function multiple times. Actually, I'm going to disable this breakpoint. There we go. We can run this any number of times. And we're going to be making all the same steps over and over again, which is less than ideal. Okay, there must be a better way. And of course, that better way is to compile stuff. So that's what we have up here. what this does is it tracks how many times it's seen the same bytecode. And if the count is higher than a certain threshold, it will check, has it already compiled the script? And if it has, then it'll run the compiled script. If it hasn't, what it'll do is it will compile the code, but as it's compiling, it will still run the code until it has an existing script. And then the next time that it appears, we will have the compiled script. So let's see that in action. I think I have it at 10 times. There we go. So now we have a JIT script, and I just realized that oh yeah, no, this is all correct. Oh, something's buggy. Huh. Ah, right, okay, it's because 47 of the ducks got hidden. Let's go with a smaller example. Let's go back to our old one. Okay, so we've got duck, goose, duck, and let's run through the whole thing. And there we go. Okay, so we warmed up, and now we've got a JIT script. And now things are going to be different. Because before we were walking through this looped switch statement, now we're going to be going through this. And if I add a debugger here, and I run it, we check if the count is there. Then if we have the compiled script, we return the compiled script, which is run the compiled script, and we've got the script, the bytecode, and the compiled script here. And then we step, and we're done. So that's much more, far fewer steps need to be taken in order to run this code now. Instead of having code where we have to go and make all of these jumps, because you have to imagine each one of these switch statements, it's not just like magically we move up. Let's go back to the programming. And let's take a look at a different example. Let's say, and I think break needs to happen. Let's just throw together a really quick case statement, just to see what the bytecode looks like. Yeah. Is that the problem? What am I doing wrong? Let's just make a file. So if you want to try this out on your machine, you can just write dis at the top and then do whatever you want. I think I can just write a switch statement like this. You know, I actually have a really fantastic switch statement that I can just copy paste. So I will just do that rather than making everyone suffer with me. I wonder if that'll be enough. We can't run anything with interpreters right now because that'll die. Okay, cool. So we have this bit of bytecode emitted, and you can see how much it is. What we have here is we have jumps that are happening all over the place. And what these jumps are doing is it's telling the compiler where to go next. And this is a lot of overhead. Let's take a look at that same code if we removed all of the case statements. It always takes a long time to open files whenever I switch here. So of course, this would only happen if we sent in a string of A, B, C, D, but you get the idea. This is also the limitation of compilers. They are specialized for a specific piece of code. Let's run it now. And what you can see here is that the bytecode is much shorter and we don't have any jumps. We're just going through what we need to do and that's it. Compared to before, where this is substantially longer. We're getting up to 231 offset, whereas in this one we're at 118. So it takes up a lot less space, we're doing a lot less in terms of instructions, and it's faster. That's the difference. Okay, let's go back to this example. And there's a couple of features here. One is that we are using a simple counter to see how many times we see a certain function. And once we reach that threshold, we then compile the script. And this is true for the baseline compiler. This is true for a lot of things. In fact, in terms of getting into the baseline compiler, the thing that we're counting is the number of times that you enter a function, not the number of times that you enter, the number of times that you enter a function and then loop back into it. Like, not the first time you go into the function, but you've called it at least one more time. That's when we start counting. And then as we go up in the tiers, we change what we're counting. So for example, we start counting at the block level at another point. But this is of course a simplified example just to allow you to see what's happening. Let me see, I should have a example code for you in the actual code base. Let me see if I can find it. Let me see if I can find it. I can't spell. This is going to be a theme. Okay. Is it warm-up counter? Yeah, here we are. We're checking here if the baseline interpreter is enabled, and if it is, we increment the warm-up counter. And that's exactly what we've just seen. So this is the same thing, but in the C++ code, I think. Yes, in the interpret function. And this is for loops. I think there's another spot where this happens. But yeah. Okay, what else can I tell you that's interesting about this? If we take a look at the compiler, which is just a simple object in this case, you can see what the threshold is. It's currently enabled. We have an incrementer here that increments the specific script. So we look up the script and we create scripts with a counter, a compiled script which is set to null until we compile it, and then the bytecode that's associated with it. So Jackie is asking about, we only start counting on the second entry. How does that work? We first have to exit the function and then re-enter it, and that's when we start counting. I think maybe one of the JIT engineers might be on the chat and might be able to more clearly explain that, because for me this is also new. I'm JIT learning as I teach this. Okay, so right. Okay, so finally there's this last bit that I want to show, which is the compile code script, the compile code part of the compiler, which is, you'll notice it's also got a switch statement in it. So doing something very similar, but it's recording its output as it does so. And the other important thing about this is that it shares the same instruction set as the interpreter. So it's sharing some information there. And that's also true of certain parts of the SpiderMonkey compiler, where we share instructions across implementations. The baseline interpreter and the baseline compiler share a lot of information. And the instruction set is very simple. It's very trivial here. Okay, cool. So does anyone, if anyone has any questions, please ask, and either I will answer or someone in the chat will answer. Let's continue on and take a look at what was wrong last time and what's been fixed. Okay, so the part in the interpreter is mostly right. This bit that we did is mostly correct, but I did make a mistake, and that was in the opcodes. I had this set like so, because I was like, oh, it's going to be fine. And I also had this comment removed. And these were both big mistakes because it meant that things were not compiling. And for good reason, because, and let's take a look at where this is defined. So here at the very top, if you're curious about learning more about SpiderMonkey, you can always search for this thing called smdoc. This is going to give you foundational information about how certain pieces of SpiderMonkey are built. And this one tells us about how bytecodes are defined, because bytecodes are defined as macros. And they have certain fields in them that are important that I ignored. Namely, n-uses and defs. The number of stack slots consumed by the bytecode, -1 if variadic. Variadic means if it can change, it varies. And number of stack slots produced by the bytecode. So let's take a look at the bytecode that we wrote and think about it a bit and think about why it was wrong. Okay, so the problem here is our stack is actually two things. The object that we are looking at to identify whether or not it's coercible, and then the property name value, which is the thing that we need to transform into a key. Now, here is the problem. We actually don't remove the object. We keep it on the stack because it's important for the evaluation later. If we don't have it there, we can't access the thing that's held in the key on that object. And I had it written differently, which is wrong. And on top of it, remember this slot, so 1 is equal to, oh, what did I do? I did something wrong. This is n-uses. And this here is n-defs, which we saw at the top of the file in the smdocs. And I will call out the comment that was made that is breaching something that I consider really important, that we keep this professional. Please don't ask about my relationship status or comment on my appearance, because this should be a safe space for people to learn, and those kind of things can be very hostile. Let's keep it professional. Okay, cool. So the problem here was that the number of uses, the number of things that we use on the stack is 2, and I'm saying that it's 1. So we should update that to say 2, and the number of definitions that come out of it is 2 rather than 1. So there we go. Now that's correct. So that was one of the reasons that this code was not working. Okay. So another reason that the code wasn't working is we hadn't put the guards in place for the different JIT tiers. The thing is, if we try to compile without informing the different JIT tiers that this opcode is not implemented in them, then it'll complain. And that's actually what happened earlier. The error message we were getting was saying that the error message was saying basically, oh, this JIT doesn't know what this thing is, so we can't link it. And the problem with that was we basically were missing these case statements. Remember, everything's a giant case statement. These things are super simple pieces of code, just large loops with case statements in them, but you have to be careful with what's going into them. So I didn't have the time to add, for example, this one. This is inside of Ion Builder, which is the top tier at the moment of the engine. And we also didn't have it in the baseline code gen, and I've added it here with mega fail. The baseline, we have two types of baseline thing. One of them is the interpreter, and the other one is the baseline compiler. And they're separate, but they share a lot of the code. They just have different responsibilities. And then on top of that, there was one other thing. In Warp Builder, which is an ongoing project right now, this needs to be implemented there as well, so that Warp Builder knows not to panic that it doesn't know about a certain bytecode. Okay, cool. So that's where we should have been at the end of the last stream, so that we could run this code and see it working. So the code compiles and runs as long as I have no baseline interpreter. And now I can do something like null 0. And it works. There are a couple of questions coming up. Why don't we rewrite it all in Rust? First time. And Ian gave an answer there. Right. Okay, so why don't we rewrite it all in Rust? So there are parts of the code base that we are currently rewriting in Rust, but you have to imagine SpiderMonkey is very large, it's very complex, and when you choose to do a rewrite, you volunteer to not implement new features because while you're doing the rewrite, you're recreating the existing functionality of the system. And the other thing is SpiderMonkey right now is very modern, it's very fast, and it makes sense to, oh, that's a kava. Well, I'm going to answer the question anyway. I don't know anything about internet memes anymore. I think I might be getting too old. But I'm going to answer the question directly and completely, because that is a question. And there is a reason why we don't rewrite it in Rust. Because if we rewrote it in Rust, you as a JavaScript developer, if you work in JavaScript, you wouldn't be able to have the new features coming out of the specification, which is another thing we cover in this stream. You wouldn't have the new features that come out of the specification as quickly. In fact, we may have to delay the new features by a year or 2 years or maybe longer so that we can get everything right in the existing, in the new rewrite. So this would be a massive cost and people would become very disappointed. Another reason would be we would probably be playing catch up in terms of performance because Rust is a really performant language, but there are certain optimizations that haven't been made. For example, in LLVM, the backend for Rust, they haven't been made yet in the same way that they've been made for C++. So in some cases, the C++ code will run faster in terms of what you can do with it. So there are reasons why not to do a rewrite in Rust, but there are also reasons to do a rewrite in Rust. Specifically, right now we're doing a rewrite of the front end in Rust, and it makes a lot of sense because Rust makes it very easy to express code in a way that invalid states are impossible. That's a safety feature of Rust that's really powerful, and we want to make use of it because it'll make it easier for beginners to start working on the code base. It'll make it easier for reviewers to review the code base. It'll make development faster. So there are benefits and negatives to doing a rewrite. And for the body, for this part, the interpreter, the baseline compiler, the baseline interpreter, the Ion Builder, all of those parts are in C++ and they're going to stay in C++ for some time. But the front end is being replaced eventually. Okay, so I hope that answered the question. Let's get back to the work. Cool. Right, okay, so we have got a working version of this now, which is fantastic. But why are we doing all of this? This is a question that we need to come back to, and it's easy to forget when it's taking us 5 weeks to get through a single bug. I wasn't expecting this bug to be so big. It was supposed to be small. But it's easy to forget, why are we writing this opcode? For that, let's go back to the bug and take another look at what Andrei Bargul commented. And what he said was the problem with our previous implementation that was based on rearranging bytecodes, and the reason why he said we should implement a new bytecode to do this properly. And here he says two things. The first one is, this is very bloated. We've got a swap, check object coercible swap to property key. That's big, that's problematic. Whereas now we've switched over to what he's proposed, which is use prepare set element, create a new opcode called prepare set element, and use that. And there's a second problem he mentions, which is the error message is worse. So, before, we actually had the same error message, and you can check it in your console. So this is the error message we had before, null has no properties. It's not very informative, especially if you've got something like this. X is not defined. Well, actually, that is all right, but there's a better one. You can have instead something like this, which says can't access property 0 of null. And same thing here. Anyway, so the problem is that the information in the error messages is not as good anymore. So, for example, if we take that same example that Andrei Bargul gave us there and use it in our current implementation, now we have null has no properties also for the compound assignment case. So before we had this one, and now it's again null has no properties. That's not ideal, and that's with our bytecode change. So we actually missed a step, and we need to fix that. Let's take a look. This is the baseline, which we're going to get to in a second. Okay, so this error is coming from this function throw object coercible. Let's take a look at it. And it's defined here, and it's essentially using the C++ function called report null or undefined for property access, and in this case, it's taking 3 arguments. Let's grab that. Just realizing that we aren't going to get as far as I thought we were going to get. That's too bad. Spent too much time on my mini-jit. Okay, I'm going to go a bit faster. And here we are. So here is the three argument version, and the error that we're falling into is this one, which says so-and-so has no properties. So that's the error that we're falling into. What we actually want to get is a different error message, which is JS message property fail, which you can find here. Can't access property 0 of 1. And it is also inside of this function called report null or undefined for property access, but it takes 4 arguments, and the 4th one is a key. So I actually already have this ready to go. I'm going to copy paste. Where is it? Because that'll make it faster. Okay. Oops. It didn't work. I have too many screens. Okay, let's hope that works this time. There we go. Okay, so here we are. The thing that I just added was this. So we have this throw object coercible function here in the interpreter. So we're all in the same file. We haven't changed anything yet. And what we're doing is we've added a new function called throw object coercible property key. And it does sort of the same steps as the previous function, which is we check if the value is null or undefined. We should only come into this function if the value is null or undefined. Then we get the ID from the context. I don't actually know how that works. Whatever. Oh, no, sorry. Okay, I know what this is. C++ sometimes throws me through a loop. We are going to be setting the name of this ID, and we need the context there. ToProperty key takes this value, which isn't a name. It's a JavaScript value. It's a representation of values in the engine for JavaScript. We can take a look at it in another stream. And what it does is it does the lookup. This ToProperty key function does the lookup inside of throw_object_coercible, so that when we report is null or undefined for property access, we can pass that ID in here, and that will enable us to get a better error message. So let's take a look at that. That should work. The only problem is we need to change the header so that we have the correct information there when we compile. Okay, that should be enough. And then, so I was just in the header file. This is interpreter header. This is interpreter C++ file, the body file. And let's look at prepare lm, prepare set. And instead of doing this, we want to do property key and check value. We also want to get, this is that. And, okay, this is the one that I'm looking for, ID value. Okay, cool. And that should be enough for us to get that to work. All right, so that's going to build. I'm going to just take a look at if there are any questions that I can answer. Cool. So this shouldn't take very long to build. Right, so this is bringing us to the end of the interpreter. And probably what you've noticed is I've been running without baseline. So I've been adding a flag every time that I run the JS shell. I've been adding a flag that says no baseline interpreter. So we've got the interpreter layer. Maybe I can even draw our layers. Okay, get rid of this. And so we have, this pen is a little hard to use. We have several layers. We have the interpreter. And then the next thing is the baseline interpreter. Then the next thing is the baseline compiler. And then next is Ion. Oh, if I press harder, it works better. And what happens at each layer is we're gathering information. So this whole thing is the VM. At the interpreter level, we don't have any information. We're just running exactly the bytecode as we see it. Baseline interpreter, I think we don't have much more information there either, but we start gathering more information. We start gathering stuff like, there's a thing called inline caches. We start building those, and we'll look at those in the next stream. Then we go to the baseline compiler, which continues to gather information, and then we go to the Ion compiler, which gathers which has the top tier of information. And what we're doing at each level is we're making assumptions. And if we make an assumption that's true up until we get to the baseline compiler, we've run maybe 1,000 times at this point. And then suddenly we get a piece of code that that breaks our assumptions. Like all the way down, we're making assumptions that, let's say, a is always an int. We've made this assumption for some function. And then we make it all the way to this point, and at this point, we get a string instead. And when that happens, what we do is called a bailout, which is we abandon the information that we have and we pull back to the interpreter or some lower level where we can still execute code correctly, but we're slower again. So the goal is always to have correctness, to, if we have hot code, compile that code and make it faster. And then if we discover that one of our assumptions is incorrect, we can bail out, go to an earlier stage where we're for sure going to have the right result and start running from there again and redo the process. Okay. Getting back to programming, it looks like this is going to take a while to compile. While it's doing that, let's start taking a look at the baseline and start our implementation in baseline. Okay, and this is unfortunately going to be a little fast because we're running out of time. I, again, scheduled too much content. So what we want to do is we want to implement this in baseline. And I just need to have my info ready, my notes. Okay. And what we're working with inside of the baseline interpreter and compiler is the same set of instructions, well, in many ways, similar instructions to what we were using in the interpreter, and we'll be doing a call into the interpreter to avoid doing inline caching, which is which is one of the optimizations that we get to do. So let's write that out rather quickly. Actually, I'll do copy pasting because it'll be faster and you'll get the same information and not have to watch me type. If I can find my mouse. Oh, you know what? I'm going to do this. I'm going to reconstruct it from existing code. Okay. So we have this emit to property key. I'm going to grab this information and I'm going to drop it here because effectively we want to do the same thing as to property key, but we want to do a step before it, which is the check object, whether or not the object that to property key is going to be called on is null or undefined. So we are going to do these steps anyway, and we're not going to do this bit of code in this session because this is the IC and this is already getting into optimization. So we're going to now look at check object coercible, which is the other bytecode that we're replacing. There it is. And here it is. I'm just going to grab all of it. And this should happen first, so I'm gonna do that. And let's read this code now that we've got it in place. Let's read it and let's understand what it's doing. So first step, frame sync stack. I didn't actually do this in my implementation. I did something different, but I didn't actually look into what frame sync stack does. So either Jan or Ian, if you can explain what sync stack does, I have no idea. But what it's doing here is it's loading a value from the stack into a register. So eventually we're going to load into this register R0. And I'm going to find out what sync stack does. I totally skipped figuring that out. But I'm going to replace this code with something different. So Jan says it ensures all values are on the native stack, not in registers. Okay, that's interesting. I'm going to have to dig into that a bit more and maybe draw it out. I'm going to drink also. Okay, cool. We're going to replace this. So I'm going to do that. And we're going to replace this because in this code, we're not going to be, what this is doing is it's taking just the value immediately adjacent to the current bytecode. So imagine we've got bytecode A, B, C, and we're here. But actually what we're interested in is in this bytecode. So the first bytecode that we're interested, this is going to be our property key. So that's the one that we're interested in. That's why it's -1 right here. And in fact, we're also going to be interested in this bytecode. So we also want to load the -2 value. But there's a shorthand that we can use for this. And I'm going to use that right now, which is frame dot. So we're going to just take the two top so what this does is we've now got R0 and R1 available to us. And R0 is going to be this one. I'm going to comment that all out. So this is R0 now. And this is R1. So we've taken values from the stack and moved them into assigned them in registers. Next, we have these two things with label. So a label in, if you're familiar with assembly, a label is something that that tells you where to jump if you've got like a go-to statement or something like this. So let's create a new layer. You've got like stuff, jump to label. So we first do some stuff, then we jump to some label, stuff, and then label. And what this is telling us is to skip this stuff, so we're not going to do this, and just jump straight there. That's what labels do. And that's what we've just created there. And the thing about labels is you often assign to them later on. This is something called patching. So jump and patch, I think it's emit, target, and patch. So what you do is once you get to the point where you can emit a label, where you can emit that this label is assigned to this address, you go and you patch the jumps that would have jumped to that point so that everything runs correctly. All right, going back to the programming. And here we have exactly what we expected. So branch test undefined and branch test null. What these are basically like if statements, like if it's undefined, if R0 is undefined, jump to the fail case. And actually this is a little interesting. Okay, this is really interesting. If it's equal to undefined, jump to the fail case. And if it's not equal to null, jump to done. So it's checking for both null and undefined. And you could use two equals here and jump those both to fail. Let's actually do that. Like you could do this and then branch, or this would be like, I don't know, I would have to look up what the exact name is. This would be a go-to thing. And we would have an immediate go-to jump. But what is implemented here is more efficient actually than doing that. We can just check if it's equal to undefined, go to fail. If it's not equal to null, then go to done, because if that previous condition is true, we'll go to fail and we won't get to done. If the second condition is false, we don't need to go to fail, we can jump to done. It's very different programming than what you might be used to. Here, what this is doing is it's binding the label that we've defined up here. As I described, once you know where you're jumping to, you can go and define what that label is. And these two are examples of jumps. Next, we have this prepare VM call. What this does is it makes sure that we're ready to make a call. To what? The call that we're making is into the, we're making a call into the C++ code. So MASM is the macro assembler, and we're writing instructions for a concrete machine, like for example Mac OS, or for ARM actually, or for Intel or something like this. We're compiling for a specific architecture, but sometimes we don't want to write all of the code that we need to do in the macro assembler. Sometimes we want to do a shorthand and then jump into the C++ code. That's what's happening here. We're jumping into C++ code here. And what we do is we push, once we prepare for the VM call, we push the argument that we're interested in, so that when we call the VM, and we define this template here with the value that it's expecting, so that we can make that call. Okay, and then we do another bind. So we've made a jump here that says, oh, if everything's successful, skip all this code that I just described to you and jump to the done. And that's what the happy path code will do. So if you have an error, the code will be slow. But if everything works, the code will be fast, which is a generally good principle to use. Okay, and then I'm going to delete this. Cool. And this should actually be different. Okay, so we've gotten to an interesting point where we've got code that actually looks pretty similar to our interpreter. So let's take another look at the interpreter. I'm running over time a little bit. In the interpreter, we actually, before I made this change, we were calling throw object coercible, which is what happened in the check object coercible. And then we updated to doing it with property key and having the ID. Now in the baseline code generator, what we're doing is we're calling throw object coercible, and that is the same function. We're calling the same function as what the interpreter used. And in fact, we want to now change that and call the new function that we've defined so that the behavior between the baseline compiler, between the baseline interpreter and the interpreter is the same. So I'm going to change this to property key, and now we actually need to have another thing here. And another thing that needs to change is we need to inform the VM of which functions from the C++ world we can use inside of the baseline compiler. And we do that in this list here. It's the VM function list, and it's a really big list, and I'm not going to go into much detail here because we are already over time. I'm going to add two functions here because we're going to need both of them. The first one is throw object coercible property key, the one that we just added. And the next one is something to allow us to implement this without using the ICs. The ICs. So throw object coercible property, we defined that together. And to property key operation. This we haven't defined. It also exists in the interpreter. We're going to take a look at it in a second, but we won't go in depth there. This is what we're going to use to avoid the IC and avoid optimization. We're going to make this super slow. Okay. So I am basically just going to copy this because we're going to do the exact same thing. We prepare the VM call. And instead of pushing the R0 argument, which is the one that we were interested here, we're going to talk about this ordering in a second. And instead of throwing object coercible, oh, and we need to change one more thing here. Because throw object coercible property key takes 3 arguments rather than 2. So, and here what we're going to do is call this other function to property key operation. Okay, cool. To property key operation, let's take a look at the definition in the text. And here we are, and it takes 3 values. One of them is a mutable handle value. And we're not going to go through these steps because actually it's a bit of a tunnel, which checks if the things are what we expect them to be. Like, for example, is this thing an int32? If it is, do this and return. Is this other thing? If it is, do this and return false. And if it doesn't work, return false. And then so on and so on. But it digs a little bit, so we're not going to go into it. Okay. But that means that we have one more item here, which we need to add to our definition of the template of the function. It was called mutable something, right? Mutable handle value. And I think I only need to push the R1 once. And the other thing I need to change is make sure that these two don't overlap. And I think that's it. I think that covers the whole implementation. So before we actually try to compile it, I will run our previous thing and show that our error messages are going to be better. So can't access property 0 of null, that's the better error message. And that's also true if we try to do this. Yeah. Again, we have the better error message, everything's working as expected. If we run this, for example, with baseline interpreter, which is eagerly done, we get a crash, which is the crash that we just replaced with our implementation. So now I'm going to make the file and hope I didn't make any mistakes. And let's chat. So we are 7 minutes over what I originally hoped for. Do you have any questions? Or what questions do you have? I'm going to be reading through your comments so far. Great. There are other people answering all the questions and better than I could, so that's fantastic. Oh, and I made a mistake. Let's figure out what's wrong. Incomplete definition of toProperty key and throw object coercible property key. Okay. And it's saying that, is there an error here? Did I forget to save? I think I might have. How to get a compiler dev job. I don't think many people can take the path that I took, because I interestingly started working on the specification before I started working on the compiler. And largely the reason that I moved to the compiler team was because I had interest in compilers. And I had quite a bit of support from my manager to make that move. For me, it was a lot of learning. So many of you know I don't have a computer science background. I'm completely self-taught, and I'm completely self-taught from the perspective of JavaScript. So a lot of this stuff about working directly on the machine, while I'm fascinated by it, I don't have the academic background for it. And I think coming from my background and applying to a job to work on a compiler, that would be quite difficult. But I think that if you start studying, one thing that I did is I did the Stanford course on compilers. And unfortunately, that course is now offline. It was very useful for me. It's basically a guided tour through the Dragon book. I don't know if you know that, if everybody knows what the Dragon book is. It's mentioned in my blog post. Compilers. Yeah, this one. So it's this book, Compilers, Principles, Techniques, and Tools. I've read the book, and I read it while I was doing the course. I did the course very quickly, so I missed some details. But if you're interested in working on compilers and you don't have an academic background, if you're like me, coming from JavaScript, I would suggest that one way to get started, if you really want to work on compilers, is start looking at something that's close to you. For example, there is a JavaScript compiler written in JavaScript, which will teach you a lot of the basics of how compilers work, and it'll be in a language that you recognize, in a space that you recognize, on a language that you know, and that's Engine 262. And the author of this project is actually in the chat. That's DevSnack. This is a great place to look if you want to get started. There aren't that many compiler jobs. It's not a super common. Well, yes, okay. Engine 262 is just an interpreter. Interpreters and compilers share a lot of features, and I think if you start coming from an interpreter is easier to get to compilers than starting without knowing how interpreters work and jumping all the way to compilers. I think it's an easier transition and it's more interactive. So, another person. Just to finish up the question about what it's like, how do you get a job as a compiler engineer, or a compiler, which is what this show is about. I think that you may need to do some background work and prepare yourself for it. Know a language really well. Maybe get involved in some of the standardization efforts, or get involved in an open source project around it. Do some secondary courses, and read a couple of books. And then see if you can get some support from within your company, or join a company that works on a compiler and see if you can transition. So, for example, the Typescript compiler, I believe, is managed by Microsoft. That's one thing that you can work on. And there are many others. So it really depends on the language and where you want to work. Okay, so there was another question, which is, did I talk about intermediate representation? And here we are. Did I talk about intermediate representation? And I'm not too sure what IL is, but I'm guessing IR is intermediate representation. We haven't talked about it yet. We're going to be talking about that soon. So far, we've just been, intermediate language. We haven't talked about it yet. We're going to be talking about that soon. What's my blog? I don't actually have a blog. I have a really bad website. It's this one, which I don't exactly use as a blog. I use it to send really bad experiments from servers to, and this is a log of really bad experiments I've done. So it doesn't have any information. Otherwise, if you want to read my writing, you can find me on Hacks. So if you go to my compiler article, there are several other articles by me that you can read, and also a number of our team members from SpiderMonkey write blog posts, such as Ian Ireland, who's in the chat, and Nicolas Perron, who helped me massively set up this session. He's also writing certain things about how the compiler works and stuff like that. Any others? Okay, cool. So everything's finished compiling. Let's take a look. I hope this works. Oh, no. Oh, I hope this still works. Okay. So let's try our original thing. Can't access property of null. Great. Oh yeah, that's exactly what we wanted, because before what I showed was, sorry, it's so anticlimactic. It's working. Fantastic. The implementation works. Okay, cool. That is all I had planned for today. So let's go into chat mode so that I can rest my voice a bit, and let's talk about any further questions you have and just chat. And yeah, thank you so much for coming. I hope you enjoyed this session. And next week, we're going to be talking about ICs. I think right now, I think that they're called intermediate cache, inline caches. Next week, it's inline caches and IonMonkey. That's what we're going to be talking about. So we'll be taking away our implementation of two-property key, doing an inline cache implementation, and then we'll be moving on to IonMonkey and Warp, and then finally finishing this bug. See you in the chat.